All right, can you hear me?
Yep, you sound good.
All right, cool. So I guess you guys are both coming in, or all three of you are coming in for homework five, I assume.
Yes, at least I
Okay.
am.
Yeah, like there, one's a more FSM, but there's one that's like you can use. One is like you can use a factored FSM because like without it, it's just like what we've been doing. But like we only had a 4-minute video lecture on factored FSM, so like I don't know if those guys are the same. Like if that was their question.
So here's the fun thing about factored FSMs. It's the same thing as a regular FSM. You just have multiple. So when you say factored, the reason why you're factoring out FSMs is because you have multiple functionalities you're trying to implement. And actually, sorry, let me turn on my camera here. Um, there we go. So the reason why you need factored FSMs is because you're trying to implement multiple functionalities. So if you're trying to detect, I don't know, an accelerometer, something that detects acceleration, and also you're trying to detect a light at the same time, you're probably not going to want to use the same FSM for both those things. You're going to want one for one and one for the other. Here it's the same concept. You're trying to detect a sequence 11010, and then you're trying to detect another sequence 00101 or something like that. Well, it would be easier for you and for the hardware to do two separate FSMs that each individually implement those functionalities. And then once you're done with that, then whatever those outputs are from each of those, then you combine them into whatever you care for. In this example, it's detect one sequence or the other sequence or both. So all you're going to do is once you finish designing the FSM to detect the first sequence and the second, you're going to take the output of both of those and you just OR them, because all you need to know is if one or the other is correct or is on. And if one or the other is on, that means one or the other sequence was detected, and that means we have to output true. So that's pretty much it for this particular FSM.
Oh, okay. So we do one FSM for the first pattern, completely separate FSM for the second pattern, and then well, it's an and for the homework, but and then and the two into it.
Well, what does it ask you to do?
It says it should detect the Oh, so I need to actually look at the book. I was just reading. It should detect the patterns 01011 and 10.
Yes. So be careful with the wording. It does say and
Oh.
while in English, yes, that's what they mean. You want to detect both the sequences. In hardware, what you want to happen is that if either of them light up, that means a sequence was detected. So in hardware, that would be an OR gate. So you can't always use the wording in English to represent the logical gates. Sometimes you can, but other times it's the exact opposite of what you think, and it can be a little confusing. So,
I see what you're saying.
so when that happens, in general, it might be just helpful to write out a truth table to represent what you want to happen. So if this sequence was detected, true. If that sequence was detected, true. If both were detected, well, that can't happen, but let's say it did. If both were detected, true. If neither were detected, off. Well, that's just the standard OR gate truth table, and that's how you go about it.
So when we're drawing the schematic, do we draw
Two separate schematics.
two separate schematics, one for each one? And then at the end, can we do the outputs from each one into another?
Yeah.
Okay,
So
got it.
you can do it a variety of ways. I would probably just draw them separately. Don't try and make them. If you have space, try and draw them next to each other, but it doesn't matter because at the end you can call this one output, say, sequence one. Well, I'm not gonna do S1 because that's like state one. I'll do maybe D1 for detected. You detected sequence 0, that's this wire, and then you detected sequence 1, that's that wire. So if you name them that, for example, and then somewhere else on your page you can say take them and OR them. That would be the easiest way to do it. That way you don't have to draw the FSMs next to each other, and it's just like doing two separate problems really, and that's all it is. It's just one. It's just two separate problems.
Okay, great. That's really helpful.
What else? Oh yeah. In general, in engineering, and just in general, when you have difficult problems, the first thing you want to do is try and split it up into smaller, easier to solve problems, and that's what this is doing. Instead of trying to design one FSM that can detect both sequences, just focus on one of the sequences with one FSM, and then you can worry about the other one with the other FSM. Okay, so anyone from Discord have any questions for me?
No. I'd like to see the example being done for that one that we're talking about right now.
Okay, so what I will say is that we went over in the office hours last time, or I don't know if it was yesterday or the last one before that, but we went over a sequence detector for, I can't remember what the sequence was, but it was something like 11010. We went over that in office hours, so it's actually the exact same thing as that. It's identical. It's just, depending on where the ones and zeros are, your transitions for the FSM might be a little different, but it's identical to that, and you're doing that twice, and then at the end, you take the two outputs and you OR them together, and that's pretty much the entire process.
Oh, that's it? Just literally just OR them together?
Yep.
Oh, okay. No,
So,
not bad,
if
then.
you want, I can go through it. I don't mind, but if
Oh,
anyone
no,
has
I'm
any
good.
other
No,
questions,
you want to.
I can go over those too. Okay. Because I do. Oh yeah, I don't know if everyone saw the message in Discord, but I did upload all of the past office hours that I recorded. I didn't record the very first Tuesday, but everything after that I've recorded and uploaded, and I should be uploading them regularly. Every night after the office hours, like around 9 or something, they should be up. So you can always go back and look at those previous ones, just in case you don't remember the full steps, or you just want to recap, or
Right.
review for like one of the exams or something. So does anyone else have any questions for anything? It doesn't have to be necessarily homework. It could just be like conceptual questions too.
Can we do the second one on the homework 5? Second
Yeah.
problem?
So the second problem, let me think. All right, give me just 1 second, because I have the book on my phone.
Do you want the book?
Actually, yeah, could I look at it real quick? Which number is it? Like 23, 28 or something?
3.28. So
Okay.
it should be on that page. One of these
Oh yeah, the gray color. That's right. And then the homework specifies like something slightly different, right?
Yeah.
Just a different sequence?
It's this one. It's just like.
Okay, cool. I'll go ahead and write the sequence up on the board real quick, and then I will let you look at your laptop again. So 0, 0, 0, 0, 0, 0, 1, 0, and then you have 0, 1, 0, 1. And then you have 0, 0, 1. And I'll do it like this. Next is 1, 1, 1. And then you have 1, 1, 0. And you have 100. And then you loop that around. Okay, cool. So I went ahead and just wrote out the sequence that was given to you guys in the homework. Essentially what you're doing is you're creating a gray code counter. So I might have mentioned this to a few of you before, but for those who don't know, a gray code is essentially a sequence of bits, and when you go from one step in your sequence to the next step, you only ever change one bit, and you change exactly one bit. So for example, you start at 0, 0, 0, going this way, you change the middle bit to a 1, going again, you change the rightmost bit to a 1, going again, you change the middle bit to a 0, and so on. And you'll notice that every single step, only one bit is changed every time. Versus if you were counting in binary, for example, you'll notice that going from step 1 to step 2, going from 0 to 1, you change by one bit, so that's good. But then going from the number 1 to the number 2, you actually change the least significant and the middle bit both at the same time. So this would not be a gray code. So that's just a little background on what a gray code is. And the point of your FSM is to essentially just take these values and I'm pretty sure it just wants you to output those values. That's it. So you have a certain number of states, and in each state, you start in, say this one, and then you move over to the next one and you output this value, and then you move over to the next one and output that one, and you keep going. And that's if you're counting up. So there's an additional input called up, and essentially what that does is if it's on, it counts in the way that I have the arrows drawn in this direction, whereas if it's off, it's going to count in the opposite direction, so going this way. Either way, it's still a gray code, it's just traversing the sequence in an opposite direction. And so that's basically kind of the background of the assignment, or of that problem. Now, given that information, we can start with our design by, again, from the steps, we have the very first step, black box diagram. So black box diagram, I'm going to do it verbally. We have a few inputs, specifically clock and reset, just the standard ones. And then I believe the only other input besides that is just up. It might be called up/down, but I'll call it just up for the sake of speaking. So like I said earlier, if up is on, we count in the direction of the arrows, and if up is off, we count in the opposite direction. So in terms of inputs, that's all we got. In terms of outputs, the only thing that we want to output is the actual position that we are in the sequence. So if we're here, we're outputting 0, 0, 0. If we're here, we're outputting 0, 1, 0. If we're here, we're outputting 0, 1, 1, etc. And so we just say, if we're in, say, this state, we output this value, this state output that value, etc. And that's pretty much it for the inputs and outputs. So we could, if we wanted to, draw a black box. And so that's our schematic diagram. So we just have the one bit input up, 3 bits of output for whatever the current code is, reset, and clock.
Can I ask a really quick question?
Yeah, go for it.
Just to go back. So when I read this, is when up equals 1 and in the other direction when up equals 0, what you drew here, is that all up equals 1?
Yeah. So if you follow the arrows, that's up equals 1. If
Oh,
you go
okay.
against the arrows, that's up equals 0.
And then, yeah, so down would be like 100 to back to 110.
Yeah, going that way,
Yeah,
going that
yeah.
way. Yep.
Okay, just making sure I understand.
Yep, that's right.
Thank you.
Okay, so now we've finished design step 1, black box. What's design step 2? What's the second thing we do? And this is open to everyone.
The actual diagram.
Yeah, we actually draw the transition diagram. So I'm going to go ahead and erase a few things. I'll get to erasing these in just a second. I'm going to leave this up because it's going to be helpful for for drawing the FSM diagram. So what I'll do is I'll start us off. I'll maybe do 2 or 3 of the states, and I'll have everyone else finish them up. But here's essentially what we want to do. So just like every other FSM, where do we start? What's the first state?
Reset.
Yes. Yep, exactly. That's the reset state. And we want to have this pretty much in every FSM, just in general. We want to have some known state to reset to. So I'll start there. And for this one, in the reset state, what code do you think we should output? It doesn't matter. You could do 0, 0, 0. You could do that one. You could do that one. Unless the problem specifically stated you have to start your very first number at 0, 0, 0, it doesn't matter. Because what's the point of this FSM? The point is it just circles through each combination of our gray code. It doesn't have any restrictions on which one has to be the first or the last. So it actually doesn't matter. It makes no difference whether you start with 0, 0, 0, 0, 1, 0, it doesn't matter. However, just for the sake of it being reset, I will write 0, 0, 0 as the very first output, just because it's all zeros. So what I'm going to do is I'm going to actually write that in this state. And I'm also going to just name the state that, just so that I know, in addition to this being the reset state, it's going to be also the state where I'm outputting 0, 0, 0. So I've named the state S000, and I also asserted my outputs as 000 because, well, that's what I want to output in that state. I'm also going to go ahead and draw my reset signal, just saying that when I reset, I go back to the state. And then now I'm going to open this question up. Where is the next state we're going to go to? And what inputs do we have to consider?
Since we went to 000, we would have to consider 010 and 100.
Exactly. And so depending on whether or not up is 1 or up is 0, we're going to go to one or the other. So from that, you guys tell me, if up is on, if up is 1, where am I going to go?
Zero 10.
That sounds right to me, just according to the way I've drawn this. If we follow the arrows, we go to 0, 1, 0. So I'll go ahead and write that in. Okay, and now just to make my life a little bit easier, if I'm in the first state over here and I have up is on, I'm gonna transfer over to the state on the right. What if I'm here and I get up is 0? Where am I gonna go? What about in Discord? What do you guys think? If I'm here and I get up is 0, where am I gonna go?
You'd go back to 000.
Exactly. And so it's actually going to be like this for most of the bubbles. In fact, all of the bubbles are going to have this back and forth action. So what I'm going to have you guys do is I'll have you guys finish the rest of them. So I've done part of the first one. I haven't finished the first one. Same thing for the second one. I've done part of it. I haven't finished it. I'll let you guys finish those ones up. I'll be back in, I want to say like 3 minutes. I'm going to go use the restroom. And then when I come back, I'll finish filling this in and we can compare our state transition diagrams. right, I'm gonna assume everyone is like at least 70% of the way there. I'm gonna finish drawing up the rest of the schematic, or the rest of the transition diagram, and then we can compare. So I've finished writing up the somewhat lopsided FSM diagram. So it's kind of like what I said earlier. It's almost identical to the diagram that I drew down here. It's just we have double-sided arrows, and we've labeled the states, and we've labeled the actual transitions as having ones and zeros. But it's almost identical to what I have labeled down here, and that's actually why I drew this diagram to begin with, because it's a nice little model to get our FSM from. But that's pretty much it. There isn't really that much more to this process besides going through the rest of it kind of rotely, drawing up the tables, doing our state encodings, input-output tables, and then current state, next state table. Then you go into the equations, and then your schematic diagram. So does anyone have any questions about this diagram? I know it might be a little hard to see on that end because of the reflections, but if you guys have any questions about my transition diagram, just let me know. Alright, I'm going to assume no one has any questions about it. And I guess I'll go ahead and get started on the next step. So I mentioned a few of the next steps. What's the next thing we should do, or the next thing we could do? What do you guys think? What can we do next?
Oh, you can do the next state table.
Yeah, sure. Let's go and do the next state table. Okay, so for my next state table, what are my inputs and what are my outputs?
Input is up, right?
And there are other inputs as well. What would they be? Or I guess things on the left-hand side of the table.
It would be the states.
The current state, yeah. I haven't made myself enough space here, so I'm probably not going to fill out the whole table, but that's fine. It shouldn't be too bad. And then on the right-hand side, what do we have?
Next states.
Yep, the next states. Okay, so I guess I'll go ahead and do maybe 3 of the first states, and I'll have you guys finish up the rest. So I'll go ahead and start with the current state being 0, 0, 0. So if we're in the current state is 0, 0, 0, and we get up is off, versus if we get up is on, we're going to end up in 2 different states. So if up is off, we're going to travel down this arrow and go to S100. Whereas if up is on, we're going to travel along the up arrow, and we're going to get to state 010. I can go ahead and do the same thing for S010. So if I'm in S010 and I get a 0, I go to S000. Otherwise, if I get a 1, I'm going to traverse right, and I'm going to get to state 011. And then I'll go ahead and do state 011 for my last few rows here. You should get, at the end of this, there are 8 bubbles. Each of them have 2 arrows, so you should get 16 rows once you finish up. Okay, so if I'm starting at S011 and I go along the 0 arrow, I should end up at S010. And if I go right along the 1 arrow, I should instead go to S001. Okay, and then while you guys are filling out the table, I'm going to go ahead and draw up the next table, the state encoding table. And did this one say if we had to do binary or one hot, or did it not care?
Yes, it does. It says, this is number 2?
Yeah.
No, it doesn't say anything about one hot. Number 1 says use one hot.
Okay, so then for this one, I'll let you guys decide what you want to do. If you want to do one hot, we can do one hot. If you want to do binary, we can do binary.
Can we do? I'll wait for them. I'll see what they want to do. I have
Okay.
a preference, though.
That's fair. That's fair. We'll do a vote then. I'm not going to count myself in the vote we have for one hot and for binary. So you're binary. Okay, one vote for
Done
binary.
like 3 one hots.
Yeah, you guys have done quite a few one hots.
I'd rather do something.
You guys have a preference?
I can do binary as well.
Okay. Well, sorry, Good Noodle, you don't have an opinion anymore. Even if you say one hot, I'm sorry, we're doing binary.
It's fine.
Okay. It's all right. You guys will get practice with both. You got a lot of practice with one hot before, so now you get some binary. Okay. So since we are doing binary, how many bits do we need for our state encodings? And as a hint, if you don't remember the formula, you can also just count in binary and see how far you can go without having to use a few extra bits. So for example, if there were 2 states, you could do that in 1 bit. But if you had 3, you'd need to go up to 2 bits.
Isn't it log base 2 of the amount of states, and then you just round up if it need be?
Exactly. Log base 2 of the number of states. And then you round up. That's the mathematical notation for rounding up. It's just the ceiling function. But yeah, that's exactly right. So in this case, how many states would that be?
8?
Not 8. Or sorry, there are 8 states. I meant to say
Oh, yeah,
bits.
yeah.
My apologies. So
Okay.
there are 8 states. How many bits would we need?
I'd say 4.
Let's try it out. So log base 2 of 8. 8 is the same thing as 2 cubed. And remember that logarithms and exponentials cancel. So you get 3. So you have 3, round 3 up. Well, that's still just 3. So you only need 3 states for this, and you can verify that also kind of not by trial and error, but by a different method. You just count up in binary from 0 to 7. 0, 0, 0, 1. So there are only 8 possible combinations if you go from 0 to 7, so you can represent 8 separate states. If we had to represent a 9th state, we would have to use an extra bit for the number 8. So we only need 3 bits for binary encoding, whereas if we had done 1 hot, we would need 8 bits. We need 1 bit per state. So with that in mind, I'm going to go ahead and draw the state encoding. And there's a few ways I could label this. I could go, say, like in order this way. I could label 1, 0, 1, 2, 3, or I could go in counting order like this. Call this 0, call this 1. How do you guys want to do it? Because it doesn't really matter. Counting order, or we can go in order of the FSM. What do you guys think? It doesn't matter to me.
I personally would think it's easier to like, oh, we're in the current stage. I feel like we should just keep it in the counting order.
So the order up here?
Yeah.
Sure.
I don't know. What does Discord think?
So that's what it'd be like if it was in the order of the FSM, and then like I said, otherwise it would look like this. So they're both kind of interesting because here you have this number paired up with kind of the wrong number, but it's in the correct order for the FSM, versus if you did it this way, it is paired with the right number, but it's not in the correct order of the FSM. So it doesn't matter in terms of actually making the problem work. It's going to work regardless. You might maybe save like a gate or two depending on which way you go. But it doesn't really matter for the process. So what do you guys' votes? You said like this. What do you guys on Discord think? Do you want it like this or like that?
No, I want it the other way.
You want it this way? This one looks more appealing? Okay. So that's 1 vote for this way.
That's the you said that's the counting order?
So this one, or so the counting order like this?
Yeah.
Okay. We'll do that one then. See what we get. It doesn't really matter. We just got to make a decision and then we're good. Okay, so as expected, because we did it in counting order, the name of the state and its encoding are identical, so we don't have to worry about that too much. Okay, so now what we're going to do is, if we wanted to, we could replace these encodings onto our next state table. And the nice thing about the way we encoded this, in terms of my writing, is I can just erase the S and we're good. In terms of writing, yeah. In terms of hardware, it might be actually more hardware. So we'll see in a bit. Well, we might see in a bit if there was anything that we could have done, and maybe it would have been better hardware. But in terms of the next state table, this is what we got. Cool. All right. So now the next thing we're going to do is we finished up our next state table. We finished up our encoding table, our state encoding table. And now the last thing is the what? It's the last table we need to finish.
The state transition table with the encoding.
Well, I just did it here.
Oh, okay.
Right. So you'd
Oh.
be correct because
Mhm.
I would have to rewrite this table with the encodings. But as it happens, because of the way that we chose our encodings, I just had to erase the S's, and now this is the encoded state table.
Mm-hmm.
So I guess the last thing I would write would be I would just write it, I guess, in that format instead of current state, next state. And so then what's the last table I have to finish?
The output.
Yep, exactly. Both of you are correct. The output table. So what I'm going to do is I'm going to go ahead and write down all of my states over on the left, and then I write what the output is for those states. And I guess I'll call it G for gray code. I can't remember what letter that you were asked to use, but I'm just going to use G for gray code. It doesn't really matter. So if you're in state 000, what gray code are you supposed to output? What do you guys think?
000.
And this is actually why it's kind of nice to label it this way, because not only is it nice in terms of kind of our FSM diagram for keeping track of stuff, but also because our state that we're in is encoded as the gray code we're supposed to output. So every time we're in a state, the actual state itself is the gray code encoding. So we don't have to have any extra output logic. What we're going to find is the inputs and outputs are identical. So in other words, you can just run wires straight from the state names, and then that's it. So we don't have to have any output logic at all. And this actually is one of the nice reasons why for this particular problem, using binary encoding is probably better, because recall if we had done one hot encoding, we would have a lot more bits. We'd have 8 bits instead of 3. And we also, normally for one hot encoding, the benefit is you don't have as much logic gates, especially for the outputs. But here you don't have any anyways because of the way you encoded it. So sometimes if you encode smartly, binary can be better just because the way you encode it means you won't have any output logic gates anyways. And that's kind of the benefit of one hot. So in this case, it happens that binary probably was the less hardware route, and this specific encoding was also less hardware. So it happens that we picked kind of the most efficient way to do it. Okay, so we finished up our diagram, we finished up all our tables. It's now the next step before we draw the schematic is we need to figure out the equations. So I already wrote the equation for the output table. That one's the easy one, right? You just draw wires over. I want you guys to go ahead and draw them up for the next state table. And I think what I'll do is I'll start writing them over to the right side.
Wait, sorry, but
Yeah.
the next state table should be like this.
Yeah, I just didn't finish writing
Okay.
it. Yeah. It should be 16 rows long. What I will say, though, is that I'm pretty sure each bit... well, that might not be true. Each bit is going to have quite a few... yeah, you'll have quite a few gates for each one. I'm trying to think how many. Because there's going to be 16 lines. I'll get to writing the equations. We'll see how many terms there are for each. It's going to be, I think, at least 3 for each of them. Maybe more. Okay, I'm going to go ahead and erase these tables. Are you guys good if I erase some of these?
Yeah, I'm good.
I'm good too.
That's going to be...
Would you go straight to K-maths with this instead of Boolean?
Up to you.
Since it's like-
But there are 4 inputs, so a K-map would not be a bad idea at all. I think that'd be a good idea.
It's like I'm getting like this.
Yeah. So since there are 4 inputs, K-map's fine. You can do 4. So for reducing, absolutely try out a K-map. It will make it a little easier. Okay, I'm going to start drawing the K-map for, I'll do S bit 2 first up in the top over here. I'll do... Alright, so do you guys want me to do the K-map along with you, or are you guys comfortable doing it yourselves? I'll take the no response as you guys are good, and I'll start filling it out myself. Alright.
check with
Yeah.
101. That shouldn't go down to 010. I think that's weird.
Yeah, that's where it is. Okay, thank you. So that would be 101 going to 0, 0. Yeah, thank you. There we go. That's right. Okay, I see. I think I'm gonna get rid of this one too, just in case. Otherwise, Okay, cool. In case anyone was curious as to why I had to change all my ones that head up as 0, it's because I was counting the wrong way. I did them both clockwise instead of one clockwise, one counterclockwise for when I was doing it, because I was trying to take a shortcut to make it faster, but I made more work for myself, so that didn't end too well. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so I finished up the K-map for S2, so in case you guys want to compare what the actual schematic of the K-map looks like, you can take a look at it. So once you guys get the equation for S2, you can go ahead and check it against what I've written up on the board, and then we can everyone can check their own work. Someone else just came into the Discord. Just so you know, we're going over. I think this is problem 2 for homework 5 that we're going over. It's the one about the gray code counter. We have the FSM up behind me as well as some of the tables, and we're just starting on the equations.
Is that for today or tomorrow's homework?
Pardon?
That's for tomorrow's homework, right?
Yeah, that's for homework 5. Yeah.
Okay.
I'll move it out of the way. Okay, so I finished writing up the K-map for S1. Again, you should be taking a look at it real quick just to compare if we got the same answers. It's very possible that I've made a mistake. It's very easy to make a small mistake, changing a bit from a 1 to 0. Very, very easy. So let me know if you guys have any discrepancies and we can walk through them together. Well, again, just let me know if you guys see anything off from what you have written and what I have written up here. And I'm going to continue working on the very last one. What's up?
Oh no, I just need to use my words.
Yeah, you're good. No worries.
Can you shift the board a bit? It's kind of hard to see.
Oops. There we go. That should be, well, maybe you shift it back a little bit because of the glare.
Sweet. Thanks.
Yep. And I'm going to go ahead and assume that everyone has at least looked at the rest of the board. I'm going to start erasing some stuff, so I'll give you guys like 20 seconds just in case you need to panic. I don't know, screenshot or something, but you don't really need to because I'm going to be uploading the lectures anyways later. So,
We can't simplify. Can you simplify these with like X symbol?
yeah. So I was going to talk about that later,
Oh, okay,
but
yeah,
absolutely.
sorry, we can keep going.
No, you're good. You absolutely can do some simplifications with XOR gates.
That's my main point, so I'm just hoping we do.
Well, you don't have to. I think for all of the homeworks and just all the problems in general, when you are asked to simplify the Boolean equation, you'll be asked to simplify it to SOP form, and this is simplified SOP form. Using XORs is going beyond that, but it is more simplified. So I haven't finished up writing the circles in the equation for the very last one because I wanted to ask how to do it. How are we going to do it, guys? So how are we going to do the circles for this, and then how are we going to drive the equation? And anyone can answer.
We have the largest one, which is S sub 1 bar and S sub 0.
That's exactly correct. Yeah, it's that second row, a full circle. And just like you said, the corresponding term for that is going to be S1 bar, S0. Okay, and then what are our other circles going to be? This time I want someone else to answer.
You can do that second column. Those two vertically.
These two at the bottom?
Mm-hmm.
And then what's going to be the corresponding term for that?
That's going to be S2. S2 bar and up.
So for this one, we have to take a look at this column. So in this column, the first term is always 0, and the second term is always 1. So we take a look over here, according to my encodings. It's a little hard to see, but I have up listed as my first one. And
Oh,
S2,
so that'd be up bar and then S2.
up bar, then S2. And then we have to look at the corresponding rows. So in the row, what are we going to have? Which term?
That'll be S1.
That's right. Okay, and the last person in Discord, what are we going to do for our last circle? Where's our last circle going to be?
The bottom right too.
Yeah, that's
It's
exactly
gonna-
right.
It's gonna be up and then S2 bar, and then it's going to be S1.
That's exactly correct. All right. So those are the three equations we get when we simplify our next state logic. And what we're going to talk about now, like was alluded to earlier, is there's some more simplification we can do here. So this is in minimized SOP form, which you're guaranteed to get if you do the K-maps correctly. But it's not guaranteed to be the minimum number of gates possible, because minimized SOP form does not utilize XOR gates, nor does it utilize POS form. So because it can't use either of those, it's not necessarily the minimum number of gates, just the minimum in SOP form. So what I'll do is I'll go ahead and start by looking at this top one, S2. So for that one, you can notice that for the middle term and the last term, they actually share an S1 bar in common, and you can factor that out. So I'm going to go ahead and write that up here. And when you factor the S1 bar out of both of the two end terms, in the inside, you have leftover up and S0, ORed with up bar and S0 bar. And for those of you who have been to the office hours, or perhaps have seen this in class, this is actually a gate. And I know it might be a little hard to see with the glare. Move back a little more. There we go. So I know it might be a little difficult to see with the glare, but these two terms actually combine to an XNOR gate. And remember that the symbol for that is going to look like this. It's just an XOR gate with the inverter right after it. And so we can actually write it as an equation like that. So a newer, simplified version of the next state S2 is. And so we've reduced the number of gates that we have to use specifically inside these parentheses. We had 3 gates, 2 ands, and an or, and now we just have a single gate, an XOR gate. So it's a little bit of a Boolean simplification, so that's nice. And so we're going to go ahead and stick with this equation for S2. Okay, so moving on to S1, for that equation, let's see. I'll move this a little bit. There we go. So over on the end over there, you'll notice we actually have 4 terms for this. And one strategy we can use is we can actually go ahead and group up terms. So if we group the first 2, pair those up together, and then we group the second 2, pair those up together, we'll notice that we can actually factor something out, and then the leftover bits will actually be XOR gates. So that's pretty nice. So for the first 2 terms together, we're going to get and then that's going to be the first 2 terms together, and the second 2 terms together will look like this. And we'll notice a similar simplification here in this second term as we did up top with this term. That's the XNOR gate. And actually in this first term, this is the XOR gate. So just in general, when you have one term, so if you have 2 terms, both which have one, I'm trying to think of the name, one variable, and you have on the left term both as true, and on the right term both as off, that's XNOR. And if you have it 1 and 1, so you have on the first term, say the first term is negated, and in the second term, the second is negated, something like this, that's an XOR gate. So whenever you see something like that, you can make that simplification. And so we're gonna end up getting the following. All right. Now, some of you might think this is where we're going to stop, but we can actually do one last step to simplify this further. And it's a little bit harder to see, so what I'm going to do is I'm going to replace these, just like I did before with A's and B's. I'm going to let up be A, and I'm going to let this thing inside the parentheses, the XOR, I'm going to let that be B. So here we have A bar ANDed with B. And then down here we have A ANDed with B bar. But from what we just said earlier, whenever we have this configuration, A bar B or A B bar, this is actually just another XOR gate. So actually, this whole thing turns out to be the XOR of three variables. So we have up, XOR S2, XOR S0. And so when we write this out, we're going to get the following. And so all we have is from that really big equation over there, instead of having, a bunch of 3-input AND gates and a 3-input OR gate, we instead have a single 3-input XOR gate to account for all of that logic, which is a really nice one. And in general, whenever you see that pattern up there on that rightmost one, or something similar to it, where you have a lot of diagonal ones, it's probably going to simplify to an XOR gate. Just from experience, you'll see that sometimes. Okay. So with that, I'm going to go ahead and erase some of this derivation, and I'm just going to leave this final term that we ended up with.
other is that the same as like the 3 odd inputs? So we could have instead of like doing all of those steps.
Yeah, so
First.
for 2 inputs, XOR and XNOR are known as the inequality and equality gates because they basically just say whether or not 2 inputs are the same or different. But for multiple inputs, they behave differently. XOR is odd parity, so whenever you have an odd number of inputs on, it outputs true. Whereas the XNOR gate is even parity. Whenever you have an even number of inputs, that asserts as true. So that's just a general thing you can know. And you can, again, recognize that from either from the diagram or if you have an eagle eye, you can spot it from the actual, from the table itself. Though it can be a little bit difficult to spot the exact configuration if you're not used to looking specifically for it. So yeah, you definitely could have seen it at the beginning, but it's just kind of hard to. It's not exactly easy to. So here's what I'll do. We're about 12 minutes over. So I'm going to leave you guys with these 2 equations, and just keep in mind that the rest of the FSM design is going to be just getting that last equation for S0, which we already have. We would just be simplifying it a little bit further, so you could stick with that one down there. After we get all those equations, we would then draw our schematic. So we have our register. So that state register has a clock and a reset signal. It has your output logic. And remember that the way we encoded this, it happens that the output logic is actually exactly the same as the states. And so if you wanted to, you can write a bundle of wires, also called a bus, as just a single wire with like a line through it that specifies how many bits it has, how many wires are in it. And then you guys would end up over here writing all of the combinational logic for these equations that we wrote up here. And then I don't know if you guys have seen this, but the C kind of inscribed within an L, this symbol, that just stands for combinational logic if you ever see that in class. But yeah, I think that's about all I wanted to go over for this question. Did anyone have any questions for me before we end office hours?
No questions from me. Thank you.
All right, sounds good.
Appreciate it.
Yeah, you're welcome.
For me, I had some like initial questions, but I can see we're way over time, and I feel like it might send like another few minutes on it. So I guess I can just pop in tomorrow and ask them.
Yeah, definitely. If there are questions about this one specifically, if it's about another one, we haven't covered any other problems today.
Mm-hmm.
But if it's about this one specifically, I'm going to upload the office hours sometime later tonight. I think they should go up like by 9 tonight. So
Wait.
if you have... Yep.
There's recordings of these?
Yeah, so I sent a message in the Discord. I didn't like at everyone, so I probably should have done that. But I sent a message in the general chat of this server with the link. Yeah, with the link to what's it called? To the YouTube channel, which has the office hours posted.
I did not know that. I will be taking a look at those.
Yes. So I have all the ones from last Wednesday until now. I obviously haven't posted this one yet, but I'm going to finish the recording and then start to upload it when I get home tonight. But yeah, if there were any questions about the earlier steps of this process, I went through the entire thing on video, so you should be able to look at that.
For yesterday or for Monday's homework that was due, did you go over like the one-hot encodings that I can like refer back?
Yes, I don't remember if we went over both problems. I think we did.
We did.
Yeah, it might have been on different days. We definitely went over one of them on Monday, and we probably went over one of them on Thursday or Friday. I think Thursday.
It was Thursday.
Yeah. So I would check the recordings for Thursday and yesterday for Monday, and you should be able to take a look at those and skip through and get to the parts that you're concerned about, or you can watch the whole thing.
Okay,
Yeah,
perfect. Thank you.
Yeah, for sure.
All right, have a good one.
You as well. Okay, I'm gonna go ahead and end the office hours. See y'all later.
Thank you very much.
You're
Good
very
day.
welcome.
Good night.
Thank you. These are great.
You're very welcome.